And what I want to talk to you about today is about bringing zk verifiers to Bitcoin using something called BitVM that some of you might have heard about. But let's start with kind of like, what do we actually need in order to kind of like do zero knowledge verification nowadays, right? So I'm using risk zero terminology here, as in you typically have, like, for example, a particular circuit or machine or program or hash of that. You have a proof, you have the committed data, which they call the journal, and then basically what happens is you compute the verification that this journal is proven by the proof as having been done by the circuit with this particular hash, or the program with this particular hash, and basically returns true and false, right? And it's probably a larger computation, not as big as, let's say, proving a zk proof, but it has a large amount of instruction steps. And the aim of this talk is kind of give you a baseline for potentially being able to develop zero knowledge verification on Bitcoin and kind of present you a few building blocks how this can probably be done. And let's start with Bitcoin Script 101, because it turns out that Bitcoin actually does have a scripting language. And once you have been learning about this, you're going to look at the EVM in a much more happier way. So basically, they have two stacks, and I'm sorry if this is very much technical depth. You can have byte vectors on them. You can have max of 1,000 elements. There's kind of like if, else, if structures. You can do the usual kind of stack operations, things you can't do on Ethereum. For example, you can pick a certain element with a particular index off the stack. You can't do that EVM. A couple of specialist operations and so on. You can do the usual comparing. But there's no loops, there's no jumps. There's 32 bits signed into the arithmetic. But there's no, for example, XOR and not invert or division, BIF shifts or anything like that, because basically Satoshi Nakamoto panicked and disabled all of them because he thought it would crash the network. There's also a couple of, let's say, opcodes, like, for example, related to hashing and signature checking and so on. And in general, it's not the most expressive kind of like scripting language, but you can do things with it, right? And one of the kind of like key things that you can't do with it is you can't concatenate two byte vectors, like, for example, two hashes together, and then hash the result of that, which basically means in practice you can't do Merkle tree verification, right? Because you need that in order to kind of like go all the way up in the tree. And this is kind of like a little bit of a joke going around that if we had this communication thing, we wouldn't have needed Ethereum. This is how the world would look like, but we are not there, and things happen in panic once in a while. If you want to read more about kind of like Bitcoin script and the opcodes and so on, you can go to this URL down here. They have a kind of like a special concept on Bitcoin because they, as you know, that you kind of like deal with if you can spend a particular value in an address, and they have these kind of special script addresses. And if anybody has better understanding of Bitcoin here than me, please do correct me. So basically, you essentially try to spend an input using a script that hashes to what this script address is, essentially. So kind of like when you're actually spending the value that's sitting in the script address, you need to send the script along. But one of the things that has kind of like happened recently is there was this Taproot upgrade. I don't know how recently it was, but it was recently, where instead of having, let's say, one script in the one script hash, instead you can have a Merkle tree. And does anybody not know what I'm talking about when I say Merkle tree here? Because it's going to come up again. Okay, good. And basically, what? The other question. Yes. Yes. And basically, when you're then sending or trying to spend the script, basically you kind of pick a Merkle path down into picking a particular script. So a particular script address can actually contain billions and billions of scripts, essentially. And there's kind of like limits on how big these scripts can be and so on, but it's kind of useful, right? And when you're sending transaction or something along with transaction, you can send script stack elements along. So you're starting to get the sense of that it is possible to do some kind of like, let's say, complex computation, but it's not fun, right? And one of the things that kind of came out recently, and this is why I'm talking about this, is Bleeding Edge. On 9th of October, Robin Linus from ZeroSync released this white paper called BitVM, where they kind of introduced three new concepts, which is called bit commitments, which is a way to keep the same value a value the same way, same across multiple Bitcoin transactions. Because in Bitcoin, well, I'll get to that in a moment. In Bitcoin, that you can't basically keep state across transactions, which is a major headache. At least in Ethereum, we can at least store something to state and then continue in the next transaction. But no, you can't do that here. Another concept they introduced was about logic gate commitments and then about binary circuit commitments. And kind of like, there's almost 1,000 people in the BitVM Telegram group, and they didn't even, let's say, do any kind of token offering or something like that. So it's quite amazing that it captured the imagination of quite a lot of people. And the first thing, and now we're getting into the details here, right? The bit commitments, it basically gives you a kind of way to have, let's say, write once memory across multiple transactions. And as I said, it's important because like cross-transaction state was not possible in Bitcoin before. So the thing here is that if you commit to a particular value, you can't just go ahead and kind of like open with a different value in a different script, because then there's a system where you get penalized for it, essentially. So it's a little bit like, let's say, more optimistic manner of doing things, that if you get caught doing fraud, then you'll lose a deposit, for example. And essentially, the kind of like primitive that you're building here, because is basically that you consume 2 hashes and the pre-image of one of the hashes, and then it puts a 0 and a 1 on the stack, essentially, according to which hash actually matches in the pre-image. And based on that, then you can kind of like start moving a little further, which is about making logic gate commitments, right? So as you know, any computation can kind of like be built up using logic gates, right? So here, for example, with this script, a Bitcoin script in this particular case, you're kind of like you're required to reveal the bit commitments A, B, and C such that A, NAND C, and NAND B holds, right? And of course, we can have many different kinds of types of gates here, right? Like you have AND, which uses the ball AND operation, or XOR, which uses maybe a little untraditionally uses num not equals, but it turns out the truth table for that is actually the same, and not, right? And if you have that, well, then you might think that you can start making kind of like fuller circuit commitments, right? Like you have input coming in, which is bit commitments, then they might have stack elements, which are then treated kind of like the intermediate states in the circuit, and you have the outputs, which can also be bit commitments in this particular case. So you can kind of combine everything together, having inputs and outputs, and you can kind of then also start having a circuit that executes with input from one circuit, like a circuit with input that's based on the output of another circuit, right? Not everything needs to be, let's say, not all these circuits need necessarily to be logic gates. For example, that one of the things that Bitcoin script can do, and one of the few things that it does really well, is adding 2 32-bit integers together, for example. So naturally, then you can start handwriting circuits, and I'm sure there's people that like to do that, but personally, I like to compile things. During this hackathon that we were originally building this stuff in, we found a 5-year-old undocumented academic software that basically compiles using compiles C into Boolean circuits, which is very nice because then you can actually use a coherent humane language, if you can call C that, and using essentially something called bounded model checking, because like if you want to check the bounds of all the loops and all the kind of transitions that happen in a program, essentially what you're doing is bounded model checking, and it turns out it's exactly a Boolean C circuit it actually yields. And one of the things that it also does nicely is that it comes with a circuit simulator, so I don't need to spend all my time and all my money on sending things to Bitcoin or Bitcoin testnet. I spend time hand editing things, right? So now we can basically make circuits from C into Boolean circuits and convert them into Bitcoin script, right? So one of the kind of like things that I made beyond this was a script that kind of like converts one of the output formats. It's a simple circuit description format or something like that, also by some crazy academics, into Bitcoin script. And right now, of course, there's limits in the inputs, outputs, amount of gate outputs on the stack, and we can get into a point where automatically we convert the circuit into bigger pieces. I kind of stitch them together with bit commitments, but you know. But there's also people that handwrite circuits, like I don't know if you people possibly said, but seen, but yesterday the BitVM team successfully ran the Blake tree hash in Bitcoin script using this technology here in a single transaction, not in an optimistic manner. So it actually, these kind of building blocks with all the bits and gates is actually good enough to get some kind of sanity into Bitcoin transactions. Okay. And this was thing about bounded model checking. We have to unroll loops, like there can't be any kind of like, let's say, unbounded loops in it. We have to inline function calls, etc., etc. So you can get down to this Boolean array. Now, basically now we can kind of do things the completely hard way, right? Like we do all the computation on Bitcoin, which is expensive. We basically go in and kind of like execute the circuit, we evaluate a true and false bit, and basically that decides if we can kind of like allow or disallow a particular spend, right? And this is where it starts getting a little magical. And basically when you're setting up the initial script address with the circuit in here, then a prover and a verifier, and all the BitVM stuff is between a prover and a verifier right now. It might be extended to more than this, but right now it is like it is. Prover and verifier assigns a number of 2 out of 2 transactions that kind of forces the prover to move the value that's locked in the computation to, let's say, the actual computation step transaction. So for example, you could have, let's say, a string of circuit executions happening essentially. The verifier can also not just be a single person, but also be an MOM signature. So we kind of rely on this being one honest party that has forced that he's not going to go out and sign on his own, that the prover can do something else. And at the end of each computation, at the end of doing the computation, then the prover is then, those of you who know what optimistic rollups are on Ethereum, basically the prover is required to wait for a week for somebody to challenge that you actually did fraud, unless, let's say, that the verifier goes and says, I actually agree with this computation result. We don't need to actually do computation then, right? Also, if you have everything in one big expensive script, then we don't need bit commitment necessarily. This is maybe something where we can fit in a zk verifier. Also, there's not going to be a single bit of zk math in this one. I'm just talking about building blocks here. Yeah, so I talked about that you can step in to challenge abuse of bit commitments and basically kind of ensure that the prover can't spend the value that's sitting in there. And then after a week, basically the prover can do what he wants because he can spend the input. As I said, now we can run large amount of computation on Bitcoin, actually express it in a nicer way than it is currently in Bitcoin script, and we can implement it with handwritten circuits or C compiled to Bitcoin script, right? It might be we can actually fit a nice little zk verifier in that. But there's also the chance that this doesn't fit at the moment, right? So if we can't complete a zero-knowledge proof verification within a Bitcoin script, within these constraints that I listed before, then we probably need some kind of virtual machine on top, right? Which kind of like is set up as a number of connected circuits, and then use something like optimistic proving in this case, right? Like optimistic proving is basically, and I'll get a little into the detail of this, finding a particular machine state of disagreement, and then run a single step of the computation of Bitcoin. So you don't need to kind of do the whole computation, you just need to do one step of it that you actually disagree about the result of. And why I think we possibly need zk verifiers here, because there might be limits on things like inputs, commitment amounts, and so on. So it would be nice to kind of also be able to do this in a zk way and kind of stuff everything into, let's say, a single transaction here as well. But just going down into machine state localization, right? Because let's imagine we have a virtual machine here, and the entire state of the machine is kept in memory, all the registers, or the current program count, or everything, right? And what we can then do is essentially take the entire memory, every word, every page, as in 4K, for example, and put it into a Merkle tree, and then essentially what we do is that we're proving the transition from a previous state where we agreed on something, plus a memory write, and that it becomes a new state, right? So this is basically why Merkleization helps, because we actually have a little bit like infinite amount of memory we can potentially address as part of this step of the virtual machine. And what I was talking about before is basically that the BitVM team got actual hash function working here that can actually go in and take two 32-bit inputs, and basically it now has become possible to at least do Blake tree-based Merkle tree proof verifications on Bitcoin script, which is much more than most people have been able to do without kind of going in and modifying the Bitcoin network, which we know is very conservative and very hard. And let me continue a little bit down. Like between a proof and a verifier, there's basically just kind of like three different scenarios. Like we agree on the result, as in we don't need to do anything. We just co-sign that this is the correct, let's say, output of the computation, which is essentially in most cases because the idea here is that fraud is supposed to basically be too expensive for you to actually do, right? It might be that the verifier kind of like times out, that during the protest he basically just goes away, he's not doing anything, and the prover can then go ahead and actually go settle it because, well, he's right then. It might also be that the prover in this particular case is doing fraud, and he times out because he can't actually prove that he's doing the computation right. And his fraud gets caught, and then kind of in case of fraud or the verifier wasting the prover's time, then that's basically, for example, the idea of a deposit that can actually be slashed. Now, bisection. I don't know if you ever have played around with Git, but they have a nice little feature called bisect, where you kind of like you state, is this block present in this particular code, in this particular point, and it kind of helps you out narrowing down the exact commit that you actually the bug started happening in, right? And similarly, we can do this with machine state. So we always assume there's kind of like an agreed starting state of the computation, which is the state on the machine that we agree on. And in this simplified version, there's a kind of max amount of computation cycles that we're doing. And then we do a little bit of a dance here, right? Like we do basically a binary search on chain, where first the prover posts his belief at a particular cycle number, what the state is, and basically the verifier then posts, do I believe this state is correct at this point? And essentially, as you kind of get down, for example, let's say we're 3 million steps, this is about 21 bisection steps, then essentially you'll end up finding out which state did they agree on and which state afterwards didn't they agree on, which basically means that you can go in and run the step that I was talking about before, because we have something we agree on, and then we find out who's actually, let's say, the winner here, right? And this, on Bitcoin, this is something that can also be enforced with these 2 out of 2 signed transactions, like I was talking about before, way before anybody has actually put any value into the address. So, as I said, that we have found an agree state, one disagreement. And essentially, what the prover does is kind of like sending what we call access logs, right? Because let me make an example with a CPU. Like they're reading the current state of the registers. They might do some operation and then write out the registers, for example, right? So you kind of like need to make a list of kind of like the logs that are accesses that this computation is supposed to do, and together with that, basically, you then check that against the agreed state hash. Is this value that we're reading, is it actually correct? Is it Merkle proof verifications? It can be a multi-proof. And then during the computation, then we go in and check updating essentially the Merkle tree based on having the siblings available. And we end up in a new state hash after the computation is done. So when we are going through the computation, basically we check in this access logs, is it actually the values that we claimed were written or read? And it actually matches with what's in the state, right? So the blockchain is kind of acting as a judge in this particular case. And then, as I said, then we can kind of compare it against what the prover is claiming and to conclude who's the winner of the dispute. And this step could basically be anything that kind of fits within a reasonable Bitcoin computation. And one of the things that the BitVM team is currently doing is kind of working on a toy virtual machine to kind of document how all this flow works. So I'll now jump to a little more my topic here, right? And I want to talk a little bit about RISC-V. Basically, and I'm going to presume you don't really know what it is, but it's an open standard instruction architecture. It has an open source license. You don't need to pay to use it. There's tooling support in all major compilers in Rust, in bin utils. There's kind of 32 and 64-bit variants, and also 128, but it's not completely sealed. And there's kind of different instruction set variants underneath, like for example 32 registers, 16 registers, floating point support, multiplication, division, and what you call kind of like GC, which is kind of like general purpose, as in essentially you can run Ubuntu on it, as compiled for RISC-V. And it's sorry. And it's kind of like super simple, kind of like to implement for basic instructions. It might be some people have had university courses about kind of how to build a CPU using MIPS or something like that, but RISC-V is really, really easy for people actually to implement in practice. And the nice thing here is that you can use, reuse existing RISC-V compilers, and also you can kind of reuse the entire set of existing test cases, like which are open source, for this virtual machine that you're building using RISC-V, which means basically less time to production. So one of the projects I'm working with is called Cartesi, and I want to talk a little about what they do. So the typical kind of reactions to most communities is when there's new computing environments is that they say, yes, let's make a custom VM, right? And as some of you might have seen in, like, let's say one of the most recent blockchain projects, for example, the EVM, basically it leaves a multi-year thread of dead projects and broken developer experience relating to this virtual machine. And wouldn't it be nice if we can actually use real programming languages and real tooling and like the last 40, 50 years of experience in this field? And this is basically why not pick RISC-V instead, right? So one of the things that Cartesi is doing is they're having a deterministic virtual machine that implements the full, let's say, general purpose RISC-V in this particular case. But they also have something that's a little curious here, right? They have what they call a microarchitecture, which is basically the smallest RISC-V implementation that is essentially able to run a step of the bigger emulator on top. And having such a small subset of CPU basically makes it quite ideal to kind of implement as a circuit. And because it's a deterministic machine, it's something where you can kind of like ideally, it's deterministic, it's Merkleized, it kind of makes it ideal to kind of do bisection on it, and something that has been done already in Ethereum and so on. So anyway, one of the things that we did in this hackathon project was basically making a 64-bit RISC-V circuit in Boolean circuits. So basically it took this C++ implemented tiny microarchitecture step and translated it into C, and basically built it with this toolchain that we were talking about before. So, and then implemented access logs based on that. So we kind of managed to get a single step in about 74,000 gates. It's actually smaller nowadays, like 30,000 gates. And then used exactly the same test suite as we are normally using the virtual machine with to validate that this circuit is acting correctly by basically putting all the access logs in and checking if it actually yields the same values all the time, right? So it becomes very nice to kind of like go in and check that this actually worked compared to making your own test cases, your own instruction set, and so on. So basically, if you're thinking about making a virtual machine, please think about just using RISC-V instead. It's much simpler. And kind of like our next steps from here is kind of like dividing the circuit now into kind of like more like fetch instruction, decode the instruction, execute the instruction, do memory access, register, write back, like steps that could potentially even bisect on chain, right? And then you can slowly start seeing that this is actually something that can actually potentially run in Bitcoin script or separate scripts. So now we get to the actual zk part here. About now you have the building blocks where you can actually make computation, you can compile, you don't need to kind of make your own instruction set. You can handwrite a Boolean circuit for it, linking it to other circuits. You can take your zkVerifier code that's probably not in C because people tend to use Rust nowadays or like other kind of like sane languages, and try to make it something that fits into, let's say, a single transaction or multiple transactions requiring kind of like challenge times in this particular case. You can try to make something that built using, let's say, BitVM's virtual machine. You can implement a kind of toy VM that then emulates certain parts of the zk verification process, like, let's say, if there's Merkle tree lookup or and then kind of like bisect it over yourself if you want to make your own virtual machine. But it also might be that I think that this is actually start happening in the near future, like closer to January at the moment. You can actually go in and even compile your zkVerifier to something like the 64-bit embedded environment, which is RISC-V, basically taking it as is and running it on top of Bitcoin, and using that as kind of like the way to actually verify certain inputs and so on, and who knows what it can be used for. Or if you want to kind of like go this easy way, which I also think is going to be possible, and if you're wondering if it might actually be possible to run Doom or something like that on Bitcoin script, it might actually very realistically be possible, because basically you can compile to the general purpose 64-bit RISC-V in this particular case, run inside a Linux kernel. Oh, and we're also running Linux on Bitcoin here. Bisect it down to this microarchitecture step and basically prove it to the Bitcoin blockchain as kind of like one of the steps in the optimistic verification. And you can even literally like build something like the RISC-0 verifier, which is basically Rust. It compiles to WASM or something like that. You can also compile to RISC-V and it will actually work, right? And just want to also talk about things that I didn't cover in here, because there's a lot more tricks that kind of like coming up here, like exact structuring kind of like the Bitcoin transactions, because I'm not going to claim to be an expert here and people might really lose money by the advice I'm giving. One of the things that's still be kind of like figured out is kind of like how do you deal with having multiple verifiers, because what happens if, let's say, the prover and the verifier colludes in this particular case. The traditional way of doing the optimistic proving is about catching liars, as in that this prover or this is lying and this verifier won, but in fact you want to get into a situation where you call it to catching lies instead, and there's an interesting research paper here. As in that somebody claims the computation ended up in a particular step, but anybody can participate in the game to find out who's actually, let's say, like what claim is actually correct. So it should be more about catching lies instead of liars, because then it's permissionless. There's no particular roles. One thing that's happening at the moment is that this thing I was talking about with Opcat, about concatenating things, it seems like people have finally stopped resisting about it, and they might actually potentially add it to something like Bitcoin, which basically means you can start quite easily doing Merkle tree proof verifications. And the last thing is also that one of the interesting things you can build with this taproot thing is you can kind of do lookup tables, because, well, it's essentially a giant Merkle tree, right? So let's say that you have, let's say, 64 bits of bit commitments. You can then pick a particular script and then look up in that single script, that what is the value that this particular value should this particular circuit should give when it comes out, a little bit like let's say a ROM or EEPROM or something like that, where you have an address line and then you basically get an output out, which makes some of these things a lot simpler. And I can see the pizzas are coming in 10 minutes. And if you want more information, well, you can find me on Twitter or on Telegram. If you want to read the Bitcoin, not the Bitcoin, BitVM paper, but you should also read the Bitcoin white paper just for good measure. You can find it here. They also have a very nice GitHub. If you want to read more about a Cartesi machine and kind of like the circuit work that we're doing, you actually see the C implementation of this and how it converts into circuits, then it's this address. And if you want to kind of get into the BitVM Telegram, then it's this address. Any questions? You probably won't be at this point.
So let me translate it. Let's say running Doom. So let's say someone is doing a competition.
Yes.
The first person to win the game on nightmare level, skill difficulty level, gets 1 Bitcoin.
Yes.
So then they run augmented version of Doom for an hour. Then the prover works for a few weeks.
Yeah.
They probably have a lot of memory because they keep
No. You don't need to keep track of all the structures in this particular case. So I can tell you how that we have actually done Doom in this particular fashion on Ethereum. So I'm going to tell how your solution works on Ethereum, right? So essentially the input is basically like your inputs over time into the game, right? So it happens in deterministic fashion here, right? Like, so the non-deterministic data is what's being uploaded. Then you go out and say that, well, we start out with the machine, it has to do them. You do all the, let's say, the key presses at the right time during the execution. And you can, well, this is deterministic execution and ends up in a particular state, right? And it basically says, well, this was the highest score, for example, right? Then you have a starting point and you have an end point here, right? And you go on and say, you go to the chain and say, well, this is the inputs that I'm giving here to the machine. So we have the agreed steady start point. And then basically, if is there anybody that disagrees about the result is this, right? If there is, you basically start going and finding about what exactly computation step is it that we disagreed about, right? And that tiny execution step, well, it starts up here, it starts up the completely general purpose emulator, and then we go a little further down to bisection, right? It's a little bit like narrowing down in a binary way, and we get to the micro instruction here instead, and that's what we are running on Bitcoin.
Can I ask you additional questions before we go further?
Sure.
So what is the step? Is that the whole state of doom then?
No, the step in this particular case is basically the Merkle root of the state of the machine, right? Before and after, right? That's kind of like the input to the step here. And then basically the prover then goes out and says that, well, I believe this computation ends up in this, and I'm providing the kind of like the accesses into the memory, and then the step executes one single cycle of the computation.
Okay, but the computation is what exactly?
Well, in this particular case, it's a RISC, it's a RISC-V instruction. So basically, you go in and read from a register. Well, you fetch the instruction, you decode it, you read from a register in memory, you do an operation. It might be that in this particular case, it's writing out to memory as well, and you write out to a register, and then basically the step is over, right?
So from the whole state of doom, you pick what is relevant to
the actual to the specific. Yes. Yes.
Yeah, makes sense.
So you said the current solution, sorry, is basically for two parties.
Yes.
And I was wondering, what will it take to make a multi-party? If you have any thoughts on that, if, will it require some breakthroughs in the state of the art in zk or some other field, or is it rather technically feasible, but we just haven't figured it out yet?
I think that people haven't completely figured it out yet, but there has been a couple of, let's say, at least getting it up to a point that is a committee of verifiers where you just need one of them, for example. But I think that the guys are kind of like checking it out. But even if you get it up to a state where that it's about between a prover and a verifier, right? It might be that this is like a little bit like between two football teams that are fighting against each other, right? It might be that then it becomes not about, let's say, that you're putting, let's say, two players up against each other, but it's part of a wider tournament. And then you kind of like find out this way and focus more about catching that's a lie rather than catching who's the liar. But basically, in this particular narrow subset of Bitcoin computation, it's 2 of 2 at the moment. If there might actually come more.
But there have to be a game set up that both sides have proper interest.
Yeah.
I have one more question. So coming back to the definition of step. Mm-hmm. So some steps might require to get data from the memory.
Yes, which is basically like I was talking about the access logs, right? So the access logs in this particular case will say this address and this value, right? And then what I need to do is when I get to that point and I'm doing the computation, I need to then go and say, okay, so this is actually the state of the memory at this point, right? In RISC-V, it's a little easier because it's divided into 2 separate stages of computation. You read from memory and you write to memory, right? So it's all separate. So they're kind of like getting in all the registers and writing out to memory afterwards. So you kind of like are able to kind of catch issues quite earlier. But essentially, it's a Merkle tree lookup, right?
But that one depends on the bit commitments, which
yes,
an economic incentive thing. So
yes,
why do it?
Yes, but the Blake tree thing that you saw there, that actually made Merkle tree verification possible, They don't use bit commits there, bit commitments there.
So how can you keep state across transactions?
Well, the output might be a bit commitment. So if you want to have it kind of like mixed in with other things, but the actual hashing function was just basically a binary circuit in Bitcoin script.
And it fit into one transaction?
Yeah.
Oh wow. Do you know how the bit commitments work? Is it some sort of an elaborate fraud proof?
It's basically like you're putting two random values, right? One of them, if you open the commitment, it reveals that this is, let's say, the value 1, right? And if you reveal the other one, it's the value 0. But if you try to open both, then you're committing fraud.
How do you prove that?
Well, there's, long story short, there's that your deposit is sitting in a taproot address where all the different bit commitments is sitting in. So basically, you go in and prove that one single one is wrong. If anybody here is asking me what this is useful for, I have no idea, but it's fun.
One last control question, if I get it. So the prover and verifier kind of needs to be able to run forward, need to be able to navigate to any part of
the computation, yes, but because it
to be able to replace the DOM to any single instruction count.
Exactly, but that's not a. Honestly speaking, that's not that's not slow.
Yeah, and then just using the input.
Yeah, so basically you basically run for X amount of cycles, and then at that point, that's when you do the Merkleization. Well, you need to do 2 Merkleizations of state. But if it's just about between 2 different steps, it's basically starting with the state you agree on, and then updates to the tree, so it's not that heavy.
So you time it by instruction?
Yes, like RISC-V has cycles, they call it.
Could you have real commitments?
Like, in terms of doing something like KZG commitment, right? If you can get it into C, we can certainly try.
So the bottleneck would be like something like a gas, I don't know about Bitcoin, but something like a gas limit, right?
Yeah, that's because obviously it's more expensive, like the more, let's say, computation you want to do on chain, right? And there's also a limit to some extent about how much you can have on the stack and so on. So you need to kind of like make it fit in, but it's not like methodically, it's not that terribly different than, let's say, doing embedded computing, right?
I mean, if you can verify a Merkle proof, if you can verify 30 Merkle proofs, you already can do a fry. So
Yeah.
So I wonder why they use the bit commitment.
A bit commitment, well, because it's not nice to have those huge scripts because there's limitations on them. Bit commitments are useful also in terms of bisection and so on, but it might very well be that you get down to a very tiny virtual machine in this particular case that's useful for some things, right?
How about continuations? Could you do that? Something like RISC-0 continuations instead?
Well, I did actually think about this when I was building it. Like during the hackathon, we built a circuit which had like 4 kilobytes of RAM and it basically did continuations, but you can do a lot of things. All right.
No more questions?
Besides, where's the beer?